This is an example video of an existing project to show a typical workflow with SpectroCalc2. It is a dataset of the H-alpha area of Gamma Cassiopeia. The observation was 2020. Before SpectroCalc, I used 5 different software packages for data reduction, and the time effort was several times higher. Let's start SpectroCalc2. I made 13 spectra images, each with 2 minutes exposure time. SpectroCalc loads all 2D images into the memory and analyze and scan the spectra automatically. This takes time, depending on your PC performance. I use a master dark with the same temperature and exposure time of my dark library. Save it as master dark. SpectroCalc corrects all 2D images automatically with the dark. I have 16 flat field exposed. I correct the flats with a master bias because of the short exposure time and the low dark current of my camera. Save the master dark for the flats. The dark correction of the 2D flats is automatically applied. Save the master flat and it is automatically applied to the 2D spectra. In case of Gamma Cassiopeia, it would be possible to calibrate with the telluric lines. I have better experiences with the reference lamp calibration. To be able to correct temperature shifts, I made between the spectra images a reference lamp image with the internal argon neon lamp of my Lyris 3. Also here I use my master bias for dark correction. In the most time, the automatic spectra scan is done perfectly, but I recommend checking the result of each spectra and correcting it manually in case of inaccuracies. Zoom in and jump to the left and right edges of the image to check the angel and the center line of the scan. Here it is perfect. Check from each spectrum the left and right side. In this case, no correction is necessary. SpectroCalc2 generates also the sky background areas automatically. However, I define it always manually. To find the border from the sky background to the spectrum, I reduce the scan to 1 pixel and switch off one of the areas. I set the active area closer to the spectrum. You can see that now the emission line is visible in the graphic. It is too close to the spectrum stripe. I set it in a safe distance. In about the same distance, I set the other area. I turn it to 10 pixel span for average. However, this is individually. Because I expect to have only small shift in the Y position between my spectra, I apply it for all. I check the last spectra if it is in a similar Y position, otherwise I have to set the areas for each spectrum separately. Only for the display I normalize the spectra to align it in the y-axis. You can see there was not really a temperature shift between the single exposures. Anyway, I try to align the spectra in the x-axis. I use the reference lamp spectra for alignment. There was a visible improvement in this alignment. Now we are finished with the first step and can save the result. The calibration tool starts automatically. There is already loaded the right calibration list of the H-alpha area. You can see the similar view of the reference picture and the lamp spectrum. Defined lines with sensitivity 3 shows an acceptable result. I select the first known line and select the according wavelength. Then I define the last line. Each known line between the wavelength is found automatically. With this number of lines, we can turn the polynomial to grade 4. The result looks very well, but let us try to improve it. I select the line with the biggest deviation. I try to define the line borders in a higher segment of the line. Yes, there is a small improvement. Now we try to improve this line. No, the result is now worse. I remove this line from the calculation. Next line. Perfect. Now I'm happy with the result. We are finished with the calibration and can save the result. 1:1 resolution is enough for my requirements. I need not all single spectra for further processing. The sum only is for interest. The post-processing tool opens automatically. First step is always the correction of the instrument response. I use a reference spectrum from LUD, Gamma Cassiopeia. Now we can define the right parameters, but I worked previously on this star and have a stored parameter set. Let us check if the parameters fits for the actual spectrum. Yes, it is perfect. The brown line shows the instrument response curve. Apply it. Next step is the normalization. If you are working together with other observers, this value should be predefined. In my case, I have already stored this parameter set. Here we see two areas, one left and one right of the H-alpha emission. The normalized value is an average of both normalization values. In addition, my preferred crop area is already stored. For the signal-to-noise calculation, I use always the same area for this object. It is 260 in this spectrum. The equivalent width area is also predefined in this project. Now we complete the header information with my stored presets. I recommend calculating always the heliocentric correction value. I do not apply it to the spectrum, but the value is entered in the FITS header now. At next we add the documentation. Title and legend. We find all important information in the automatic generated legend. If you want, you can modify the text by selecting and pressing the Enter key. Now we are finished and can save the end result. This is an uncut video, so you see the complete processing needed less than 15 minutes. You find all necessary 2D files in a link below of this video. Please view also the 3 tutorial videos. Thank you for watching. Servus and ciao.